Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel, we cover all things Gen Chem related. On this video, we're going to be covering things like colligative properties and understand how adding solute to different solvents impacts things like vapor pressure, boiling point, and freezing point. Let's get started. In this video, we're going to be discussing what are known as colligative properties. Colligative properties are those properties that actually depends on how much solute is present, not necessarily what is there, but how much is there. As we add more solute into that solution, those solute molecules are able to interact with the solvent, and it's going to prohibit or maybe enhance certain things that are possible. And so we need to have a good understanding of what is being placed into a solution, how much is being placed, and what impact it could possibly have. Now, the vapor pressure of solutions is one that is impacted by having additional solute added into a solution. As you add more solute into solution, well, those solute molecules are able to interact with the solvent molecules. And so what happens is you have less of that material that's able to get into that vapor phase. The result, when you're dealing with comparing the vapor pressure, which again, remember, vapor pressure is the pressure that's developed as you have these gas molecules bouncing off the wall. Well, when you're adding more solute into this and you're lowering how much things can get into that vapor phase, we would expect that the vapor pressure of a solution would be lower than that of a pure solvent. And so we can see this, that there's going to be this change in equilibrium that's happening as we get things going into solution or into the vapor phase, coming back out, and you'll have some lowering that's going to be occurred. Okay. And so just remember, a concentrated solution will draw solvent molecules towards it due to that natural drive for materials to mix. And similarly, a concentrated solution will draw pure solvent vapor into it due to its tendency to mix. The result, the big thing we want to remember when we're adding in more solute into a solution is that the vapor pressure of that solution will be lower than the vapor pressure of the pure solvent. All right, and you can see this depiction here where we have pure solvent versus a concentrated solution. Again, vapor pressure is based off of those gas molecules being in vapor phase and bouncing around in this particular container. And so if you have additional solute particles that have been added that can now can connect to the solvent, well, it's going to prohibit how much can actually get into that vapor phase. So again, you're going to have lowered vapor pressures with solutions compared to those pure solvents. Okay, and you can see again, less vapor is being created in that solution scenario. Now, vapor pressure isn't the only one that is impacted as we add these solutes to the solvent. We also see a change in the boiling point of a substance as well as the freezing point of a substance. And we're going to really delve into both of these two topics and through a series of calculations as well. But the thing that we want to remember when we are adding in solute, well, again, those solute molecules can now interact with the solvent molecules, which means that's something else that we need to break apart to get things into the vapor phase. And so what you're going to see is that you're going to have much higher boiling points for solutions than you would for pure solvents. So we're going to elevate the boiling point. For the freezing, it's actually kind of the same, but just going the other way. In the freezing situation, we now have, again, more molecules that we got to deal with, stripping more energy out. And so if we have to do that, the result is that the freezing point is going to be lowered or depressed, as you're going to see in a few slides. Now, if we look at the vapor, the phase diagrams for a solution versus a pure solvent, we do see that there's this shift in where the temperature would lie for both the boiling point and the freezing point. Again, your boiling point is going to be elevated in a solution, and it will be, the freezing point will be depressed in a solvent. So one of the things that we see, or where we see this happen, is when we think about salt water, right? We know that water tends to freeze at 0 degrees. However, if we looked at the freezing point of like salt water, well, it freezes at much lower temperatures than just 0 degrees. And that's because you have these added molecules that we now have to strip more energy out to get them to slow down in order to form that solid material. We also see that happen if you live in a cold region where we're throwing salt down on the ground. Well, the reason we're adding the salt, it's not, a lot of people say, oh, we're going to melt the ice by adding salt. Well, really what that salt is doing, it's helping to lower the freezing point of that liquid that it's ultimately around. So the water will no longer freeze at 0 degrees, it'll freeze at a lower temperature because we got to strip more energy out. So we can do a calculation to calculate how much the temperature will change based on the solute that we're adding. And this calculation is based on a freezing point depression calculation. And so what we're expecting is that the freezing point of a solution will be lower than the freezing point of a pure solvent. And we can calculate that through a very simple calculation where we can say the change in temperature that we expect to occur is going to be equal to the molality of that solution times the Kf, which is the freezing point depression constant. So that's something that's specific to the solvent that we're dealing with. Now, our freezing point depression constant has units of degrees Celsius per molal unit. And so we end up with molals canceling, and we end up with degrees Celsius as the unit that we would obtain from here. So then we could compare that to what the solution is, and we know that we're going to subtract that from whatever the solution freezing point is to predict the new freezing point. The great part about this is the same exact equation is used for boiling point elevation, but we just change it from the freezing point depression constant to the KB, or the boiling point elevation constant. Okay. And so on this chart here, you can see a variety of KFs and KBs, those constants provided for you for different substances. And you see there's a huge range that exists for these things. You can also see what the normal boiling point, normal freezing point is. And that's what we would expect if we're dealing with a pure solvent. But as we know, as we add more of the solute, we're going to have a shift in these materials. Okay. So if we think about what is the freezing point of a 1.7 molal aqueous ethylene glycol solution, well, what we need to know is, all right, so if it's aqueous, that means we're dealing with water being the solvent. So we know water should freeze at 0 degrees. However, when we add this ethylene glycol to it, we expect that there should be a decrease in the actual freezing point. It should be depressed. And so we can calculate, well, how much is that temperature going to change? By saying the change in temperature is going to be equal to the molal times the freezing point depression constant. And so if we don't know that value off the top, we could look at our chart on the previous slide, or as you can see here, the Kf for this would be 1.86 degrees Celsius per molal. So our delta T in this case would end up being our molal number, which is 1.7 times that Kf value, which is 1.86 degrees Celsius per m. Okay, and so when we calculate that, we end up with 1.7 times 1.86, and that gives us a change in temperature of 3.162. Proper sig figs, we'd say 3.2 degrees Celsius. Now, that doesn't mean that's the temperature. That's just how much it's going to change. And so we could then say, well, I know the pure solvent is 0, and I'm going to now subtract out 3.2. And so my new freezing point should be negative 3.2 degrees Celsius. Okay, so you can actually calculate what that new freezing point would be. Okay. And we can see, again, it makes sense in terms of the numbers that we're seeing. All right, so this one says, calculate the molar mass of a compound if a solution of 12.0 grams dissolved in 80 grams of water freezes at negative 1.94 degrees Celsius. So again, some context clues for us here. We know that water is the solvent, and we know the freezing point of water should be 0 degrees. However, we're seeing it at negative 1.94 degrees Celsius. So what that tells us is the change in temperature was 1.94 degrees Celsius. We've lowered it by that amount. And so now how are we going to go from this change in temperature to help us to predict the molar mass of something? Well, normally when we're looking for the molar mass of something, we know we could go to the periodic table. But what you should notice is we don't know what this substance is, so we can't go to the periodic table. So what we need to do is somehow determine the grams per mole of this material that we have. We have the mass, right? It's telling us 12 grams, but what we don't know is how many moles that's compared to. So we can get there by taking advantage of the fact that this change in temperature is equal to the molality times that Kf value. The reason we want to use that is because, well, molality we know involves moles. And so if we could get in there and tease out that unit, we would be in a good position. And so now if we're solving for our molality, the molality would equal the change in temperature divided by our Kf value. And so that would be 1.94 degrees Celsius divided by 1.86 degrees Celsius per molal. And that gets us 1.94 divided by 1.86. And that gets us 1.04 molal. Okay. Well, so now we got to figure out, well, how do I tease out the moles? Remember that molal is equal to the moles of the solute divided by the kilograms of solvent. So if we want the moles of solute, we would take that molal value times our kilograms of solvent. So our molal value would be 1.04 times, well, we don't have the kilograms explicitly given to us, but we know how many grams of that solvent we have, how many grams of water. So in kilograms, that would become 0.0800 kilograms. And then we can solve accordingly. So we'll take our 1.04 times 0.08, and that's going to give us 0.0832 moles. And we're almost done. The last step would be to take our gram amount, our 12 grams, divided by our moles. And that will give us 12 divided by 0.0832. That'll give us 144 grams per mole. Okay, so a lot of steps there, but again, we're just tying in those units that we see. Okay, look for those natural ties between those units. Okay, good. All right, so we can apply the same concept when we're trying to see how the boiling point is going to be impacted. And so a lot of people, if you ever watch any cooking shows, you'll see people sprinkle salt into their water to help make it boil faster. They always say that online or on TV. But in reality, it's all that the salt is doing is helping your noodles not stick. It's actually just making the boiling point of your water even higher. We're going to be elevating this boiling point as we add those solute molecules or particles into the solution. And so again, same exact formula, but now that change in temperature is going to be added to whatever the boiling point of the pure solvent is. We expect it to go up. Okay. All right, so let's try this problem out. It says, how many grams of ethylene glycol must be added to 1.0 kilograms to give a solution that boils at 105 degrees Celsius? So a lot of information here, but it's saying that, well, we have water, so that's our solvent. We know the boiling point of water is normally 100 degrees, but it's boiling at 105 in this case. So what that tells us is the change in temperature here would be 105 minus 100 is 5 degrees Celsius. Okay. So then how that helps us out is we know the change in temperature. We can hopefully deduce out what the mole amount is through the molality, and then we can use that Kb value for our water accordingly. Again, if you don't remember the Kb value, you can go back to that chart. And in our case, our Kb is 0.512. I'm going to write that down right here so we can reference that as we're calculating. Okay, so we can now plug in and say, well, our molality would be equal to our change in temperature divided by our Kb value. So that would be 5 degrees Celsius divided by 0.512 degrees Celsius per molality. So that would be 5 divided by 0.512, and that gives us 9.77 molality, okay? Well, so if it's 9.7 molality, remember the molality is equal to the moles divided by the kilograms of solvent. Our kilograms of solvent in this case is 1 kilogram of H2O, which therefore means our moles would be equal to 9.77 moles of the ethylene glycol. So now if we wanted to get the gram amount, we would simply take 9.77 moles of C2H6O2 and then multiply by that molar mass. So 12.01 times 2 plus 1.01 times 6 plus 16 times 2 for the oxygen. So that gets us 62.08 is to 1 mole. And so if we now multiply that by 9.77, what we end up with is a total of 606.52. For sig fig purposes, we could round this off to 606 or 607 grams that we would be adding in to this substance, okay? This problem says calculate the boiling point of a solution made by dissolving 1 gram of glycerin in 54.0 grams of water. So again, boiling point means we got to figure out what that change in temperature is. And that we can calculate by taking the molality times our Kb. Before we can plug in, our molality is going to be based off of the number of moles of glycerin that we have. So we'd have to first calculate that. So need that molar mass. So 12.01 times 3 plus 1.01 times 8 plus 16 times 3. And that gives us 92.11. That would go here is to 1 mole up here. Okay, so that would end up being 1 divided by 92.11, and that gets us 0.0109 moles of C3H8O3. For our kilograms of solvent, we got to take that water, that 54, and divide it by 1,000. So that would give us 0.0540 kilograms. So then our molality is going to be that mole value divided by our kilogram value. And so that'll give us 0.0109 divided by 0.054, and that will be 0.202 is the molality. And now we plug that into our formula to calculate the change in temperature. So it'd be 0.202 times that 0.512 degrees Celsius per molality. That's from before, that's the constant for water. So 0.202 times 0.512 gets us a total of 0.103 degrees Celsius. So is that our answer? Well, no, that's just telling us how much the temperature is going to change. If we were dealing with pure water, the boiling point of pure water, we know would be 100 degrees, or 100 degrees Celsius. Well, now if it's changing by 1.103, that means that our boiling point is going to be equal to 100 plus that 0.103, which gives us 100.1 degrees Celsius, or 10, as our new boiling point. Okay, again, a lot of steps here, but we're just connecting the dots with those units. All right, one last topic and then we're done. So one of the things that you guys may have noticed as I was walking through those boiling point and freezing point problems is that we were dealing with all molecular compounds, right? There weren't any ionic compounds. But remember, colligative properties are based off of how much of a substance is present, not necessarily what it is. Well, with ionic compounds, remember in ionic compounds, when they're placed in solution, they ionize, which means we now have more ions that are floating around than the original ionic piece that was placed in there. And so we have to take into account, well, how many of these ions do we have floating around in solution? And so that's where these Van Hoff factors come into play. The Van Hoff factor is simply a ratio that we're going to be using that represents how many moles of the solute particles are present as they've dissolved. This is simply going to be determined by looking at the ionic compound that you have and figure out how many ions would it be after it dissociates. Whatever that value is, that value would become your Van Hoff factor. And so how we're going to incorporate this is when we're doing these change in temperature calculations, we're really going to be multiplying by I times the molality times the Kf for the freezing point, or I times molality times the Kb for the boiling point. In the examples that we did previously where we had a molecule, a molecular compound, it's only one. So the I would be 1. But for like an ionic compound like sodium chloride, when that ionizes, I get sodium and I get chlorine. So our I factor would be 2. Okay, so we have to take that in mind when we're dealing with ionic compounds. Okay. And so you can see here in this chart the predicted Van Hoff factors for several ionic compounds. Again, for a non-electrolyte, a molecular compound, the I value is 1. But for something like sodium chloride, well, when it ionizes, I get Na plus Cl. So I get 2 ions, which is why the I is 2. For something like magnesium chloride, well, now I'm going to get some magnesium ions with a 2+ charge, and I get chlorine ions, but I have 2 of them. So my I factor would be 2 plus 1 gives me a value of 3. So ionic compounds, we have to add that I factor into these calculations for boiling point and freezing point depression. And we're going to do an example here. Okay. So the last problem that we're going to cover. So it says, calculate the theoretical boiling point of a solution made by dissolving 10 grams of sodium chloride in 54 grams of water. Okay. So again, we're calculating the change in temperature. We're now going to have to take into account that Van Hoff factor in order to solve this. Well, because it's sodium chloride, we would expect that the I value would be 2. There's 2 ions present. For the molality, we're going to have to calculate that. The molality is going to be the moles divided by the kilograms, moles of solute by kilograms of solvent. So our moles of solute we can calculate by taking our 10 grams of sodium chloride and using our molar mass to get to the moles. So we would take 10 divided by 58.44, and that's going to give us 0.171 moles. To get the molality, we then can take our 0.171 moles and we'll divide by the kilograms of solvent. So again, divide that by 1,000 or move that decimal point 3 places. And that'll give us this many kilograms, 0.054. So we plug that in. Okay. And so we take 0.171 divided by 0.054, and that gives us 3.17 as the molality. We then can now calculate, well, what's the change in temperature going to be? And now we include that Van Hoff factor, the 2, times the molality, times that KB factor of 0.512 degrees Celsius per molality. Okay, so now if we plug that in, we have 2 times 3.17 times 0.512, and that gets us a total of 3.25 degrees Celsius. Again, that's not the temperature, that's just telling us the change in temperature. And so we know water typically boils at 100 degrees, but we're now adding in this 3.25. And so we would end up with our boiling point at 103.25 degrees Celsius. Okay, so 103.25 degrees Celsius. I hope this video helped. I know it was long, but I hope this video helped you guys understand different colligative properties like vapor pressure, boiling point, and the freezing point. Make sure you guys like, comment, and subscribe, and let me know what other information you would like to see from my channel. Come back for more videos. I'll be doing a series of Chem Quicks to help you guys in your studying, as well as a lot of different practice problems for you in the future. Have a great day, and I'll talk to you guys later.